Okay, good morning, everyone, and welcome to the Field's COVID-19 seminar. I'm going to hand you over to Jianhong Wu, who will introduce our speaker today.
So good day to everybody across the coast to coast. It's a privilege to introduce my dear friend, James Watmough, one of the most senior, despite his relative youth, mathematical epidemiologists in the country. And I say so. I have had great pleasure of collaborating and interacting with James since the SARS time, and we've been working together on SARS, creating my test project, the Center for Disease Modeling, and this Canadian National Task Force for COVID-19 Rapid Response Modeling. So today I'm very pleased to having to be the speaker of this last seminar for the year 2020. So James is talking on epidemics, endemicity, and herd immunity. James.
Oh, thanks, Jianhong. Yeah, it's good to be virtually at the Fields Institute, I guess. Maybe one day we'll get to go back there for actual meetings. We'll see.
Nice year.
Yeah. I want to do a sabbatical in Toronto in the fall, so hopefully I'll actually be able to do a physical one. Anyway, thank you for the invitation. Much of the work out here is in New Brunswick is supported by, well, recently by CAHR through the Mathematics of COVID-19 Task Force, but mainly my work supported by NSERC and of course UNB. But I guess a lot of the, gotta give a lot of thanks to Fields and Arms for supporting workshops and just all kinds of support for modeling, epidemic modeling in general. But I think what I decided I would talk about today is not actually going to be anything about the funded research going on. So none of the work that's supported by all these organizations. I was thinking it would just be a good time to just go do some simple epidemic models and look at the simple models again at the end of the year, see sort of where we're at, remind ourselves, and then look at, well, hopefully we're heading past the epidemic mode of this pandemic, and then we can think about what happens once we, towards herd immunity or endemicity, and just remind ourselves what the difference between all these terms are, right? So much of what I do, uh-oh, that button didn't work. Aha, that's the button that works. Good. The objectives here really are just looking at the simple SIRS model and see what that tells us about herd immunity and vaccination. So I'll do a quick review of the SIR model. Really just, so looking at the list, yeah, so probably something everyone's familiar with, but just to remind ourselves what the basis of all this is, and then look at the SIRS model and just play with some simple things about where we're going to go with this in the next year or so. And I suppose mainly, most of what I do is theoretical and abstract, but so there will be nothing really specific to SARS coronavirus 2 or COVID here, but I'll make up some numbers that might not be entirely unrealistic, I guess, to get some ideas what's going on. So first, let's start with some terminology. Epidemic. I won't use this too much really, but the difference between an epidemic and an outbreak as I see it, outbreaks usually mean something local, small, containable, a small outbreak. And the epidemic is something that is spreading through a whole population, right? So you see it in a disease like this coronavirus is going through a almost completely naive population, right? And so some of that is also the difference, the thresholds that we get in the deterministic epidemic models would be thresholds for epidemics, but you can have lots of sub-threshold outbreaks, right? With the that you would see in the stochastic models, right? So a lot of the outbreaks we see with measles, they're really just outbreaks, the reproduction number is kept less than 1 through vaccination, but we still see lots of outbreaks, right? So I'll mention that just to remind ourselves that that's there. But the real focus I thought is worth going into is the difference between the epidemic and the endemic, right? And in particular, so endemic, I imagine everyone's familiar with it, but you never know who's going to watch this recorded lecture later, so we'll see. The endemic is the term you use for a disease that is permanently circulating in a population, right? So measles, chickenpox, those are endemic. This coronavirus, the new one, isn't endemic yet, but we do have, what, 6 other seasonal coronaviruses that are circulating? Endemic, right? So this new coronavirus is invading an existing system of human hosts with other coronaviruses running around, right? And so there'll be interesting interactions between those as this whole thing unfolds and we head more towards an endemic, right? And so part of this talk is just to remind ourselves why we don't want to naturally approach this endemic. And I'll get into the probably two ways we can approach this endemic or this later stages of the end stage of the pandemic. One is by loss of immunity, right? So you get the SIRS model, and the other one is with demographics. So those are both ways that you can have new people coming into a population, either through loss of immunity or through birth, new fodder for the pathogens, right? And then, of course, the SIRS model, we'll see that there's a lot of opportunity for seasonal forcing, right? And there's a lot of work been done on seasonal forcing in these types of models. Not sure why I mentioned that there, just because you see the oscillations, I guess, but I'm not going to actually stretch into that just so I can keep the focus on the endemicity and the herd immunity, I guess. Right, so just quickly to remind ourselves what we were, what all these models are based on. The simple SIR model, we subdivide things into susceptible, infected, recovered, and assume things are all homogeneous, assume that the infections are caused by contacts between susceptible and infected, and that the rate that you get new infections is just somehow proportional to the number of pairs of susceptible and infected people, right? The product S times I. But in reality, of course, what do we lose on this simple model? One is the heterogeneity in the population. One is that these flows between compartments are stochastic. That's an easy one to put in. And one is that the rates of both infection and recovery are age dependent, health dependent, all kinds of dependencies, right? So, but essentially, all the models we've seen, or a good chunk of the models we've seen over the past year that have become popular and everybody's looking at for their talks, are variations on the simple SIR model, right? My favorite one would be just dividing the infected population into 2 groups, one who are symptomatic, one who are asymptomatic, or if you like, some who are undetected but infected, and some who are detected, right? So the I might be detected, the A might be the undetected, and then your P would be your rate of detection, or rate either detection through development of symptoms or through contact tracing or something, right? And so this is an easy way to put in a time since infection, right? You progression through here. So if all the, what do I have here? I guess I can use my little pointer thing. If all these alphas are the same, then you get nice little Erlang distributions for time spent infectious, right? And of course you can weight the different, either weight things differently, so you have different rates of progression through these compartments, or rate the detection rates, either symptom development or probability of being tested. You can weight those by roughly by time since infection, right? So you can build quite a bit into these things. But essentially, as long as the incidence term is a linear combination of all the numbers of people in the infected compartments, multiplied by the, I guess I should say, as long as the force of infection is a linear combination of that. So then you multiply that by the number of susceptibles. And as long as there's only one route into infection here, or one type of nonlinearity in the model, if you like, essentially these are all just variations on the simple SIR model. So the important thing to keep in mind is we still have essentially the same results for the final size and the threshold that I was going to talk about here, right? Right, so I think that's, oh, I still have more background here. And so again, really I want to, my goal here is to head towards looking at herd immunity and endemicity and then remind ourselves what the difference between those two is. So we're just building up a bit of background just to remind ourselves what is going on with these really simple models, right? So the simple SIR epidemic model, you start with an initial susceptible population, introduce a small number of infections, and you get this classic curve, right, in the IS plane. And so the final size is just the number of people. I always think of the final size as the number of susceptibles remaining at the end of the day, but it's the 1 minus that, essentially 1 minus the fraction of people who were still susceptible, right? So the fraction of people who were infected. And all of these models, the I here might be some non-negative linear combination of all your different infected types of infected people, but essentially you get the same type of thing going on, right? In a lot of these models. And I think we probably don't need to say anything more about reproduction number because that's been said in all kinds of talks all the way up through the year. But the one thing, so I kind of like this, so even maybe not relevant all over the world anymore, but a lot of this theory for the thresholds reproduction number depends on linearizing your model, right? And so at the start of an outbreak or a start of an epidemic, we linearize the model. So a lot of these forecasts of what the epidemic is going to do over the short time would be results of a linearized model too, right? But also certainly in Atlantic Canada now, and more or less over a lot of Canada, I think the cases are still small enough that you can get away with doing this linearization and pretending that the number of susceptibles is constant, right? We're still on those initial stages. We're trying to stall the pandemic at the early stages to buy time to get a vaccine, right? And get this vaccine distributed, right? So we can linearize this model, right? And the solutions are, of course, exponentials. And so if you have a fancier model, you'll still get some fancy multi-exponential in here, right? Or some other interesting creature if you put delays in. But with a simple model, we're still seeing this. We get, so for example, the new strain that's come out of the UK, the news reports seem to say that it's a 60 to 70% more infectious, which as far as I can tell is referring to the reproduction number. But I think we'd have a lot better luck conveying what's going on to a larger number of people, I guess, if we switched away from thinking about the reproduction number to back thinking about these growth rates, or in particular doubling times, right? So this is kind of just an aside plug for thinking about doubling times of epidemics still. And so it's an easy thing to do, right? Basically, the reproduction number, as long as you, well, essentially the doubling time is easier to see from the incidence, right? And so what we do now is we need to sort of do some computations from the growth rate through the duration of infection, this alpha, right, and compute what the reproduction number should be. But I was trying to, the numbers coming out of the new strain in the UK are still kind of not entirely sure what they mean. But if you have a, it seems to be that the reproduction number has increased from, for this one particular strain, increased from about 1.1, which is presumably a reproduction number with lots of community measures in place, to 1.4, so something like a 70% increase. But if you look at the doubling time, just from rough back of the napkin calculations, guessing at sort of the alpha, the rate duration of infection hasn't changed between the two strains, then you can sort of guess that that actually gives you that increase from 1.1 to 1.4 in the reproduction number actually translates to about a threefold decrease in the doubling time, right? From about, say, 20 weeks to 5 or 6 weeks, right? So you can see that it's a huge change in the doubling time, right? So it is a lot more believable that the one strain, a new strain, can take over from an existing strain if things are sort of running around with the spread rate close to 0 or the reproduction number close to 1, right? So yeah, so just a back of the napkin thoughts on how best to get across the fact that is it really surprising or nasty or scary that a new strain appears and manages to become a dominant strain in seemingly about a couple of months' time, right? So it doesn't take much of a change, especially if you have a community measures in place, so you're trying to control the pandemic near this threshold level, that a slight increase in transmission can give a big advantage to a new strain, right? And all that comes out of a nice simple model, which is kind of nice. That one, right? Right, so the final size. I'm not actually sure if, a lot of the vaccination rates, this business that we need to vaccinate 2/3 to 3/4 of the population for this particular coronavirus, the business that we need to vaccinate almost the entire population to get rid of measles. This all comes from this final size relation, more or less, right? And the reproduction number. One thing to point out here that I think has come out in quite a few models, just to remind ourselves what's been done over the year. As Fred Brouwer said, this is this final size relation amounts to finding the solution of a simple transcendental equation, which of course is very sensitive to the reproduction number, very sensitive to the transmission rate when you're very close to the threshold, right? So this is the business where I think it's good to still get across to people where did we start with this pandemic? We probably started with something that was upwards of 3, between 3 and 4, at least over 2.5, somewhere in there in terms of a reproduction number. The final size of the epidemic isn't very sensitive to interventions once your reproduction number gets up that high, right? So it takes a lot of work, a lot of interventions to see some effect in the final size. To see some effect in the peak prevalence, right? But once you get close, it doesn't take a lot of additional effort to have a really big impact, right? Which is why combined interventions, you want to push that combined interventions are still very, very effective, right? That extra little bit of work. And of course that, again, all kinds of differences between models, but that basic feature is sitting in all of these models because most of the models we've been playing with are variations on this simple SIR model, right? Anyway, so that's all background. How am I doing? Not babbling too long on background here. things that everybody already knows. So we're just reminding all of you what you already know. And then the one other tidbit that I discovered, actually it was last year sometime, reading through papers, and I do not remember which paper now was the one that sort of triggered this in my head. But the nice realization that when you look at the stochastic SIR model, I've got here, and I'm not sure, this is my attempt to learn how to use ggplot and play with pretty pictures in ggplot. But you can see with the stochastic model, pushing yourself over this threshold from 1.1 to 0.9, this is the threshold that the deterministic model says you no longer have outbreaks, right? Or no longer have an epidemic. You've prevented an epidemic. 1.1, you have an epidemic. It takes a long time to unfold. It doesn't get to a very high peak, but it's still an epidemic. 0.9, reproduction number of 0.9, you don't have an epidemic. But in terms of the stochastic model, got to remind ourselves that the local outbreaks, smaller outbreaks, this is just a histogram on a log scale for the final size, right? So all of these 1, 10, 100 are just very small outbreaks. They aren't very sensitive to this switch in the reproduction number over the threshold, right? What we get rid of is a small number of larger outbreaks, right? So now I think this was, yes, I did 1,000 simulations of the simple SIR model, stochastic SIR model underlying that deterministic model, right? With 10,000 people, so small population, right? And I thought that was, so that is also something just to remind ourselves of at the end of the year, I guess, as we go forward, take a break and then get back into modeling. A lot of what people see is these smaller outbreaks happening locally, right? Or at least in Atlantic Canada, which are still going to happen and are not as sensitive to the this threshold of 1. Yeah. Right. So having sort of reminded ourselves what goes on with a simple SIR model, what the epidemic theory tells us, right? And of course, in practice, all our questions are going to be a little bit more specific than you can answer with a simple SIR model, right? Who do you target the community measures at? Which one's better? All these are not things that can be answered by the simple SIR model, which is why we build more interesting models and study them, right? But just to remind ourselves that simple SIR model, what that tells us and what's underlying all this. So now the difference between the epidemic and the endemic, I guess, right? 2 ways you can get at this. One is things like measles, chickenpox, smallpox, polio, all of these confer a long-lasting immunity, which I always, all my students, actually everybody I get a chance to talk about this with, you can't really say long-lasting. Anytime you say something is big or long-lasting or any kind of magnitude comparison like that, you've got to be in comparison to something else, right? So when we say long-lasting, it's got to be long-lasting relative to something else. So in this case, it's long-lasting, probably relative to the lifetime of the host, but also relative to the, so the immunity is on a much longer time scale than the duration of infection, right? Although I think in this comparison I'm making, it's really long-lasting and short-lasting is relative to the lifespan of the host, right? So we get almost lifelong immunity to a lot of these diseases, which is why they end up being childhood diseases, right? New infections appear in newborns, well, not quite newborns, but younger people, right? So interesting thing that you see, just as a complete aside, well, not really a complete aside, because we're supposed to be looking back at what these simple models tell us. Measles now, when we have measles outbreaks, they tend to be in high school, young adult, 20 some odd age range, right? The outbreaks pop up there. which I think kind of fits with a simple model that in vaccinating a population where for measles, we need to vaccinate almost the entire population to obtain, to get the reproduction number less than 1 and obtain this herd immunity that I'll reinforce with some equations in a second here. But the other side of that is the closer you get to that herd immunity, the higher your expected mean age of infection is, right? So what we've done by vaccinating not the entire population, but almost the entire population, is not given ourselves herd immunity and protected everybody from infection. We've just delayed the expected time to be infected. So in some sense, herd immunity, and you can see that with the age distribution of people who are being infected with measles, it goes up, right? The more people you vaccinate, the higher it is. So your herd immunity through vaccination is not a case of preventing, unless you can really push yourself over it, like we did for smallpox, and hopefully for polio soon, right? You're really raising the mean age at infection, right? So you're seeing older age groups, the epidemic appearing in older, or outbreaks appearing in the older age groups, right? Right, now the coronaviruses, all of the ones that are circulating seasonally, right? These normal ones, the ones we're used to, that are giving us the common cold all the time, those seem to have a short 6 to 12 month or so ballpark immunity. So after 6 months to a year, you've lost enough immunity from an infection to leave yourself susceptible to a new infection, right? So I don't think there's any reason yet to suspect this new coronavirus is any different. I think the jury is still out on that. And the other important thing to keep in mind now going into next year, I think there's optimism that the vaccine gives you a longer immunity, the various vaccines we have, but we don't know yet, right? So every day that goes by, I suppose we can add 1 day to the duration of the immunity provided by vaccination, right? Because we get 1 more day in all these studies of the cohorts that have been vaccinated, right? But this is a different way, so I would just want to contrast the timescales and the difference between the type of endemic you see and this notion of herd immunity that we see in the things like longer lasting infections where we have the vaccine and we're obtaining the herd immunity through vaccination, right? Versus the shorter lasting immunity and not going to a herd immunity, but to an endemic equilibrium that is compared to the peak of a pandemic, nice and mild, but compared to where we are now, the endemic is still not a pleasant place to be, right? We're still not at that level yet, right? Right. Yeah, so again, I don't think I need to say too much about the SIR model with demographics other than just to point out, so the jargon I tend to use, which I don't think is standard, is I refer to the SIR epidemic model and the demographic model as to whether or not you've got birth and death of the host in there. But of course, if we put birth and death of the host, we introduce terms that are probably on a different time scale, right? Depending on how long-lived the virus is, representing appearance of new susceptibles in the population. So this gives us another equilibrium, right? The endemic equilibrium. And we can get these threshold results this time that say not that if we're above this threshold, we get an outbreak. But if we're above this threshold, we have an endemic. So we do the reverse thing, right? We're trying to now, we have these infections, these diseases that have been endemic in the population since time immemorial, and we want to now try and get rid of them, right? So we vaccinate a certain proportion of the population, change this initial population size of susceptibles, and try and drive that disease below this threshold, right? But the important thing is everything gets summarized by R0, which kind of explains why, one part why R0 seems to stick with us, right? Why people keep measuring that is it pops up as a nice parameter in these models. It's also, in terms of contact tracing, I suppose, a nice explanation of what's going on right at the level of the person, right? Yeah, so the vaccination rate required for herd immunity, this 1 minus 1 over R0. So that is where I believe, I assume that's where we're getting these 60 to 70% of the population needs to be vaccinated to protect us from this coronavirus, right? But remember, the coronavirus is a little bit different here because we are likely, right? I mean, there's no reason to suspect that the duration of the vaccine will be any longer than the natural immunity from an infection, right? So this result here comes from the model that assumes sort of a lifelong immunity, right? And so somehow that's going to have to play in that, you know, it's going to take us till the fall or next, it's going to take us a full year to get that 60 to 70% of the people vaccinated. How does that compare to the time scale of the duration of the vaccination? Are we going to be in a situation where we have to keep vaccinating, or are we going to be kind of safe from that? So it's a bit too early to tell yet, but we can still do all the modeling for that, of course. Right. Yeah, so we don't have long-lasting immunity to those coronaviruses. So the simple SIR model isn't quite right. The SIR demographic model isn't quite right. So we want to go to these SIRS models. Right. And so these are pretty simple. We just toss in more terms, right? So this, again, the alpha here is essentially the duration of infection, and the gamma would be coming from the duration of immunity, right? So you put a simple switch of people moving from having been recovered with immunity, waning immunity, and popping back. And of course, this is the simplest, probably the simplest model of that, right? So just to remind ourselves where we're going here. Yeah, and so it's easy to compute an equilibrium this time, right? So we get a nice equilibrium where, and so I think this alpha over beta, that's essentially a 1 over R naught, right? So I think I've scaled to fractions of scaled these things to be fractions by assuming that my initial population is 1. Yeah, so all these are relative to the initial population. And then this ratio, you can think of this ratio as gamma over alpha plus gamma, right? So as it's telling me really there's a gamma over alpha plus gamma here, and there's an alpha over alpha plus gamma. So these really are taking the people who are not left susceptible at the endemic equilibrium, right? So I'm going to call this the endemic equilibrium. And this alpha over alpha plus gamma gives the fraction who are still immune as opposed to the fraction who are still infectious, right? Prevalence. So ballpark estimate, what do we expect that to be for a coronavirus? This is probably a ratio of alpha being on a time scale of months. No, sorry, alpha is the other one. Alpha being on a time scale of a week or two, right? And the gamma being on the time scale of months, right? So a factor of 10 or 20 different between the alpha and the gamma, right? So ballpark, you kind of expect once we reach this endemic of the people who are not susceptible, 90% of them will be recovered, 10% will be infectious at any given time, right? So ballpark numbers to keep in mind, right? This is where we're headed with these equilibriums. So these are, I was going to preface this with that any, this is more or less theoretical, any similarity to any diseases known to man are completely coincidental, known to humans, I guess, known to people. But I've tried to roughly get numbers just based on the estimates of the reproduction number before community measures went in place all around the world, right? 2.5 or so for 2.5 to 3.5, somewhere in there for the reproduction number. Estimates for the duration of infection. I think for these graphs, I was using about 2 weeks for the duration of infection. And then I think on these graphs, I used about a 6-month for a duration of immunity, right? So rough back of the napkin estimates of what might be going on with this new coronavirus, right? Or any coronavirus, I suppose, because they're similar numbers for all of those. So you can see that the initial, right, we're all aware of this, so just a little reminder, the initial pandemic looks the same, right? So this would be starting at time 0 here with nobody infected or recovered. Everybody's completely susceptible. This is tracing through the pandemic. So this part of the curve looks a lot like what the results of the SIR model look like, right? With permanent immunity. And so it's the immunity kicks in. Well, essentially, I suppose with these numbers, because this is about the point 6 months into the pandemic, when without interventions, we would be on the other side of this pandemic, right? This is where the loss of immunity starts to kick in, right? And so you end up at this spiraling into this endemic equilibrium rather than having the pandemic end, right? So this is essentially one guess at where how the pandemic might end in the long term over the next few years, right? So we want to now also think about what we might do with vaccination in here, right? And how all that fits into this other model. But of course, just the other, there's been lots of nice work here. This is where the seasonal forcing comes in, right? Because we have this natural frequency, right, that comes out of these simple models. And of course, we do get seasonal changes in behavior that are going to change the incidence. We might get seasonal vaccination patterns, right? All of these things will give us some nice seasonal forcing. So likely you might end up with some periodic solutions here rather than decaying oscillations, right? But just ballpark, just to remind us, so this figure I made up for a Science Atlantic talk that was given just after that Barrington Declaration. And I still keep hearing comments about herd immunity. So this would be my argument that herd immunity without vaccination, well, it isn't really herd immunity to begin with. That's the wrong notion. Herd immunity with this vaccine, if it's not lifelong protection, is probably not the right notion either. We're really going to an endemic, right? And so here I've plotted these in fractions of the population. So just using very rough numbers, but numbers that may not be all that wrong. We're sitting here at what, 5%, right? So the I is 5%. And the R is 60 some odd percent, right? So that means at any given time, roughly 60% of the population is recovered with immunity, has been infected at some point in the last little bit, right? 5% of the population is, that's the prevalence, right? When you factor in that, so you just think of the population, how many people is 5% of the population? That's a large number of people to be running around infected. And then when you factor in what fraction of those people who are infected are in the hospital, right, you can get the ballpark idea. at this endemic equilibrium at the tail end of the pandemic after we've gone through the worst of it, which is really, really bad potentially, right? Which is why we're going through all these weird Christmas, right? Nice quiet Christmases, yes, with small groups. The reason we're doing that is this 30% prevalence is just something we do not want to be at, right? Or we'd rather not be at, depending on where you are in the world. But even this 5% is pretty nasty. That's a lot of people, a lot of hospital beds taken up by pneumonia patients, right? People with these nasty complications from this virus, right? And so this is really definitely not a place we want to be. This is not really an option to consider, right? We do need to get the vaccine going. What we're trying to do now is use community measures to lower the reproduction numbers so that this number here, this point we're circling around at the endemic is closer to here, right? But we don't want to keep that on forever. We can't. At some point, we've got to relax all these restrictions, which means we will end up back here. So the only option we really have is to try and get the vaccine in place to lower this prevalence at the equilibrium and avoid this peak, right? Right. So we're using all these community measures to avoid this nasty peak, and we want to use the vaccine to try and push this thing, this endemic equilibrium, further down, right? How am I doing? Yeah, so I probably, I did do some back of the napkin things, and it's kind of cute, just a little geometric thing, essentially in adding one way to visualize sort of back of the napkin thing about what the effect of the vaccination is. You've got two options. One is that vaccination just removes people from S, if we can vaccinate them fast enough and the vaccine is long lasting enough. And then you actually do have the same, you need to vaccinate a fraction 1 minus 1 over R naught of people to push this endemic equilibrium to 0, right? Which is what you want to do. But the other option is that if the vaccine is short-lived, then eventually we're going to be in a situation where we have to revaccinate people every once in a while, right? We've got to annually take this vaccine, right? So we're basically pushing people from S, and if you don't want to make the model any more complicated, you just push people from S to R, right? Of course, there have been lots and lots of models with more complications than this, but just the simplest models tell us that basically the trade-off of increasing the vaccination rate looks like it's kind of linear, right? You basically, your null clients here, your equations you're solving to solve for the endemic equilibrium are basically straight lines, and you're just pushing one line up with a vaccination rate, right? Excuse me. Yeah, so I think that's really, I thought my goal here was just to review a bit of the SIRS model before we take a Christmas break, and then we're going to come back and do lots more complicated models on this end of the things. And I'll end here with this slide because that's my prettiest GG plot. So thank you.
Thank you, James, for your very nice review and get us sort of a mind in for the holiday season. So we can now entertain questions, and I do have a question for you, James, in the spirit of the last night. So 5% of population infected. If it is cumulative, if this is distributed over a year, then maybe that's tolerable. But if it's concentrated to a few weeks, that's the real challenge for the public health system. So
right. So this number is the fraction infected at any given time.
Aha.
Right. So then so a certain fraction of those people at any given time would be in the hospital. And, if you figure your average hospital stay is a couple of weeks or up to 6 weeks, then you have to scale that up by that factor to figure out how many people are actually in the hospital at any given day, right? So yeah, so this 5% is not pleasant, right? Because that's the current number of people infected, right? Not
True, but
averaged over any time, but the number of people infected at any given day.
so does assume that you vaccinate people at the same time.
Yeah, this one doesn't have any vaccination in. This is just the, essentially the vaccine, well,
Just reducing the
I think
reproductive.
it's probably a bit too early to figure out exactly how to put the vaccine in the model now. You want to do lots of different things because we don't really know how long it's going to last, what we have to do, and how a lot of the issues with the vaccine are who do you vaccinate, how you distribute it, how fast can you vaccinate. But essentially, the vaccination should push this equilibrium towards the origin, right?
No, but so my question is why you want to do that? That's why my question is, if you vaccinate people at the same time, that's effectively reducing the susceptible population. But if you vaccinate people at a constant rate, so you just your vaccination pace, and so would that generate a more flattened curve? I don't know. It's
It
only
should. So my thoughts on that were, at least initially, we should be able to distribute the vaccine. I mean, the limit to vaccination rates now is just availability of vaccine, right?
right. Even you have massive vaccine available, if you
Yeah,
assume that's not going to last too long, if a pace staying in different time interval, and so that's effectively just assume you have a vaccinated compartment. You have a certain rate that you can adjust for vaccination rate. Would that generate similar phenomena of mass vaccination at the same time, or just distribute the vaccination time?
um, I'm just trying to remember because that was in our paper that we did in 2003, right?
Yes, yes.
And I'm just trying to remember exactly what that, because I was thinking in terms of essentially a mass vaccination of sufficient numbers would essentially stop things in the tracks, right?
Right.
Um,
No, what I mean
but
is, if vaccinate people, if if it's recovered, if the immunity waning at the same speed, so at a certain time, this vast amount of population vaccinated is going to become susceptible, then you can see a larger outbreak because of the susceptible population. So if you spread it around the year, they might not generate larger susceptible population at the same time.
yeah, so it basically is a trade-off in the two timescales, right? Between the
Right.
vaccine timescale and the recovery timescale. That the new here is the vaccination rate, which is not quite right, right? That would say how long does a person wait before they get vaccinated? But we're actually vaccinating a fixed number of people as opposed to a fraction of the population, right? So I think
Right.
this model here is only the one you want to look at when you're at the stage where most everyone has been vaccinated and you're just trying to pick up the people as they become susceptible again, right?
Right.
Yeah.
Any other questions, comments from the audience? You can send my chart, or you can raise your hand.
Oh, I do see a hand raised. JB.
JB, can you ask a question directly?
Jacques?
Yes, yeah. So the vaccination is of effective efficacy. So 95%, as I said, is rather high compared to the flu vaccine, for example.
Yeah.
And even a few months ago, people were asked what kind of efficacy was expected for the coronavirus vaccine, and they were saying 50%. They would be very happy with 60%. And for the new ones, that the ones that are being developed, that's the figure that's being discussed. It's 50 to 60%. How difficult would it be to incorporate vaccination with different efficacy rates in such a broad model as a simple SIRS?
You would, so I think you'd lose the ability right away to just pretend that, so this simple one pretends that the vaccine is just like being infected, right?
Mm-hmm.
Which is okay for just getting a rough idea. What I wanted to do, explain what endemic equilibrium looks like versus, well, explain sort of roughly where things are headed here, but you do want to add on at the minimum. So you'd want to add on a compartment for each vaccine then, right?
Yeah, if they're so different, I
Because you'd
think.
have to have a distributed different R compartments for the different durations of infection.
Yeah.
The easiest way is to duplicate the compartments, but that's not going to quite cut it because we're going to, I assume in most of the world, we're going to, well, I guess in some places you just get what vaccine you can, but the different vaccines also have different complexities in how easy they are to move around and get to places, right?
Yeah, that's the main point of
So
these
you're going to be using different vaccines in different communities and also on different age groups, I imagine, right? And so if you really want to know what's going on, you really have to narrow down your question and figure out how much of that detail do you need for each question, right? Because I know with this, the two vaccines we're rolling, presumably we're going to be dealing with in, is it the Moderna one is about to be approved or not quite soon? So sometime in the next little while, we'll have two vaccines to distribute,
yeah.
right? But they have very different, one is, well, I was joking this morning that one vaccine, you have no problem with cold storage of vaccines up north, right? You just leave them outside. But the one I don't think we can get.
No, I mean you cannot reach -70
No.
even outside.
Yeah, so I don't think we can get that vaccine effectively to remote communities at all.
Yeah,
So,
that's one of the logistical problems that.
So I think right
And this is why
there.
some jurisdiction presumably will only use
Yep.
the new vaccine that do not require such cold temperatures.
Temperatures, right? So I think right away there, any kind of question around that, you need to look at some little bit of spatial structure, right?
Yeah.
Different community
So you have to
sizes,
different patches. Yeah.
and so at the very least, though, so the piece that's still of interest in New Brunswick is the adding on some importation of cases to these models, right? Because the situation in New Brunswick and in the territories, for the most part, is going to be there are very few or no cases, and you're introducing the vaccine, and it's a race against getting the vaccine there and how fast are cases being imported, right? And so that should let you focus on a specific geographic region with a single vaccine compartment and importation. So not much more complicated than this model.
Okay. Thanks.
Thank you, JB. I don't see the coronavirus with in your background anymore. You must be vaccinated. Other questions, comments?
I'll ask a question, James. This is Amy.
Hey.
So it's kind of, I've been thinking a bit lately about, when should we be using deterministic models or agent-based models? And like a lot of the fast response models that have been high impact papers have been agent-based models. But then today you kind of said that you could calculate R0 for, you can really just keep adding compartments. And as long as the force of infection is a linear combination of the infectious compartments, and you really just could keep going. But I wonder if it's sort of a practical issue that writing down the system of equations, you start to feel a bit silly about it once you get to like 30 equations. And it's just easier to write it down as like bullet points. We assume this or we assume that. And yeah, I don't know. Do you kind of feel the same way, or do you feel like it's
so I'm
large?
confident that even in all these, within certain limitations on what you can add in, it doesn't really matter how many compartments you add in. You're basically sitting with a special case of that Kermack-McKendrick integral equation model, and you have the results on the. So you're building a fancy distribution of the infectious period with lots and lots of parameters, right? But you still have the basic theory coming out of that. But of course, as I discovered, because I think you were at the talk Ali Garuni gave last week.
Yes.
And he has something that's actually not too much more complicated, right? So the theory is easy enough, but trying to look at the sensitivity of R naught to a specific rate is still, I think once you get past a few parameters, in my view, whether you use the individual based or the deterministic model kind of depends on the questions you have, right? Once you get past just a handful of parameters, you're still stuck with lots of numerics. And for my own stuff, I'm doing that. The simple models are fun, but I think a lot of the questions, particularly in New Brunswick, have to do with heterogeneity in the spatial and demographic heterogeneity on all these, right? Which I think is you either have to go towards a network or an agent-based model to really capture that. And you definitely need the stochastic stuff because we're still at the beginning of the epidemic and nothing's really deterministic anyway, right? But yeah, the complexity you're talking about, I think, is a number of parameters, isn't it? If we could build agent-based models with only 2 parameters, I'd be happy, yeah.
Yeah, like at some point you get an analytical solution, but it's got so many parameters.
Yeah.
You might as well have not got that. You just get it numerically.
But I know my solution exists.
I think before and during the pandemic flu season, I think there's a series of papers by Fred Brower, Pauline Wandendrich, Julian Reno, and the speaker today. Is talking about really how much the compartment model can do, and I think there's some discussions about whether it's a strategic insight or logistic implementation to some trade-off. And I think the 3 papers which was designed for the pandemic, and that's exactly discuss how compartment model compare with intensive computation intensive agent-based and individual-based model. I think the first paper is the interface.
I should read that. Thanks.
Thank you. Do you recall its lie model? SLIR? Is lie model?
Liars, yes.
Yeah.
SLIAR.
Okay, if there's no further questions, I want to thank, on behalf of the Fields Institute and Kuma, the director, and I want to thank everybody for coming, and wish you all a happy, safe, healthy holiday. And we can resume the seminar series early in January. Thank you, James.
Oh, thank you.
Thanks, James.